Hi, my name is Mike Parker, and I'm on the Symmetrics business management team. I want to talk to you about the competition, and I'm not going to talk to you about specific competitors, but rather I'm going to use a fairly broad brush and explain the difference, especially at the high end, between what we do and what the other competitors do. At the high end, if you want, let's review the design criteria. The high end, which is where the VMAX operates, is characterized by a large compute engine, an operating system, and APIs. And this is how the applications talk to your OS. So that's roughly the design. Most of the competitors out there are not high-end. And the way that you can tell is if you look at the compute engine, in many cases it's 2 nodes. So that's not a large compute engine. What is that going to mean? That's going to mean that they're going to have trouble with the function. The function is going to be a little less than what we can do. Though the feature on the VMAX that makes the VMAX is FastVP. FastVP is the function that we have in which we take storage pools, we put flash, we put fiber, we put SATA drives in a pool, pricey, cheap, fast, slow, and we group these drives into this pool, and then we organize the applications from production to maybe mail to maybe test, and then we assign these to the pools appropriately. This design ends up saving you cost and clicks, or it ends up saving you capital expense, operational expense, and manpower expense. This design is very compute intensive because the engineering behind this is that it works on a 12-track chunk. We take these 12-track chunks and we put them in the appropriate media after gathering some statistics and determining the movement. Given that there can be over 2,000 drives, that's a lot of 12-track chunks. That requires a very large compute engine to do this. But when you do this, when you have this technology, you save costs and clicks. If you only have 2 nodes, or if you don't have the correct operating system and the correct APIs, this is going to be difficult in the extreme to do. Now there's a couple of other things to keep in mind. So this is going to be difficult for just about any of the other competitors do because of the design of their compute engine and their OS. And this is a major, we're finding this to be a significant cost and operational savings. Now there's some other things to consider when you look at the competitors, and there's some basic numbers that we need to talk about. The first number I want to mention is 2 billion. And that is EMC's annual R&D expenditure. That's a lot of money. And what happens in technology ventures like this is that you pretty much go as fast as the R&D budget can propel you. In other words, generally speaking, 200 engineers will out-develop 100 engineers. And so this isn't VMAX, this is EMC-wide, but the point is that's a big number. We have over 1,500 engineers at last count working on this. Now you see where the problem is, because we're ahead. If you want to catch us, you would have to improve on that number by a lot. You'd have to get 2,000 to make a serious run at us. That's expensive as well. The other number I put up is 1990. That's when we started this. Now in a storage device, storage devices are much more complex and much more difficult than people think that they are. And the reason is because when you get this, that many drives and all of this going on, that's a very event-intensive environment. You learn things like soft failures on drives and predictive logic, and there's a lot of things you have to learn to make all of this work that having a head start from 1990 gives you a huge advantage. All of the algorithms that we developed in 1990 to deal with all of this are still in existence. We also switched that over to Intel blades, and Intel blades give us performance and they give us cost. A number of people are doing these, but they're not doing them at scale. Remember, we can go 8 nodes. We're the only people that can do that. That's a fairly significant engineering achievement, and the way that we do that, of course, is the memory-based scaling that we do. No one else can scale 8 Intel blades. It's sufficiently complex. We're not sure anybody's going to be able to for a while. We suspect eventually someone will figure it out, or maybe there'll be another technology. But right now, Intel blades look like the winner. We can scale 8. No one else can do that yet. $2 billion in annual R&D makes us hard to catch. That's a lot of engineers. 1,500 engineers. That's an expensive resource. The other situation you have is that with all the technology companies in the world, they're not easy to find. And so we recruit globally. We have people all over the globe. And when you get up into numbers that large, I'm not sure that there's another 2,000 laying around for other people to grab. This is huge. We call that cumulative man years. In 1990, we only had about 10 or 15 engineers, but in the accumulating time, the amount of expertise that you accumulate since 1990 is huge. If you're a startup, and we hear all the interesting startups and they have interesting designs and we know who they are, one of the first problems they're going to run into is cumulative expertise. Now, just because we can recover from advanced things like nested and iterative errors doesn't mean that the new guys can. They're going to have to run into the situation, they're going to have to diagnose it, they're going to have to figure out how they're going to do it, and that's assuming that they have the basic part right, which is the compute engine, the OS, and the APIs. Likewise, SRDF, for example, which is how we replicate that symmetrics to that symmetrics, maybe out of the continent. That requires some considerable expertise, because now you're dealing with network, you're dealing with multiple errors on this end, multiple errors on this end, you deal with in-flight errors. You've just got a lot of things that can happen that can make that not work. The problem at the high end is not only that has to work consistently, because this is your lifeline in case you have a fire on this end. So why does SRDF work? Well, a lot of it is because it came out in 1996. So again, you're talking 15 years of accumulated expertise and balancing 2,400 drives and 2,400 drives and the link and everything that goes on with this. Time Finder isn't quite as hard. Time Finder is where we copy that volume to that volume. That's not quite as hard, but the trick here is your partners, Oracle, SQL, Microsoft, the application partners have to know what you're doing here. The easy one to explain, for example, is VMware vMotion. So VMware is sitting over here in the Intel blades, and that one fails, and he's going to move it to this rack over here. He says, I need to move that blade there. He needs to move the storage. He pings the symmetrics, and we say, oh, okay, so that needs to go from that drive. We'll move it over to this drive because that's connected to that. Classic example of where we cooperate with one of our partners. Again, the interface to VMware, Oracle, and everybody else is a cumulative condition. So there's just some things, and then of course FastVP is just, like I said, that's the real barrier. One of the things that happens here is that if your compute engine is too small, when you try to do fast, you end up using bigger chunks, because the trick to fast is that however big your chunk is, you have to be able to do what we call hash it, or find it really fast. If you have a smaller compute engine, you can't go that small. So you have to use a bigger chunk size. You might want to use a gigabyte, for example. Well, the problem with using a gigabyte chunk is that you're wasting space. So if you got this part wrong, and a lot of them seem to have some issues, this is basically scrap and start over. If the compute engine, the OS, and the APIs aren't right. That costs money. Eventually, keep in mind that in the technology world, It's the lack of margin and the lack of revenue that eventually kill you. So, like I said, if you're going to compete with us, you have to have the big compute engine, you have to have the OS, you have to have the APIs. That one is a relatively simple case of money, but you're going to run into that whole virtual matrix memory scaling situation to get to that. Most of the conventional technology only gets you to about 2. So you've got to, we use memory scaling, you've got to come up with that or something like it to get it sufficiently large. The OS, the APIs, and these applications are all manpower intense, and they just represent accumulated number of man hours, and there's really no shortcut to that. If you're going to come after us with 100 engineers, they'd have to work 15 times more, which of course isn't practical. So you get into some numerical challenges, some financial challenges, people challenges, time challenges, where things, just because we figured out in 1993 and you're just starting out, you've got to figure those things out. So again, to wrap up, we have 2 kinds of competitors, ones that are at the high end. Usually what happens there, check the compute engine. You'll find that the compute engine is usually quite a bit smaller, and of course the reason that we have such a big compute engine are some of these applications that separate us out from the mid-tier. If they're mid-tier, they're in a whole different world. You know, they generally top off at 2 nodes, and what they're going to do is try to make this cost-effective and simple to use, which by the way is a big market. We have a product called a VMAX that addresses that market. But again, if it's critical and if it has to run, then you're at the high end, and the 2-node designs aren't going to work. So essentially what happened is big R&D budget, lots of people running start. Now we've got fast, cuts your costs, cuts your clicks, improves your capital expenses, improves your operational expenses, and this is doing well for us. So the generally speaking, the barrier to entry here is significant. So again, just to wrap it up, it's generally comes down to numbers. It comes down to your R&D budget, the number of people you have, the accumulated expertise, the algorithms, the applications are complicated, the hardware is complex in as much as you've got to be able to build an 8-node device, and you've got to be able to run something like FastVP to cut the costs and cut the clicks while at the same time maintaining your availability features.